Alrighty, folks. So today we're talking about section 5.1. So we just got done with probability, and now we're going to be talking about something called distributions, which is a way to sort of connect the probability that we've been doing to the variables and data stuff that we talked about at the very beginning. So this section is about discrete. Oh, thank you, iPad. It's good to know. I don't know how to make you go away. So we'll just sit here and wait till it decides to go away on its own. There we go. Talking about discrete random variables. So, a random variable in general is a variable whose numeric values are determined by some experiment. And that's it. I don't know why I was expecting there to be more than that sentence. And actually, that's just a random variable. A discrete random variable is a discrete variable whose numeric values are determined by some experiment, right? We defined what a discrete variable was near the very beginning of the class. It's a variable whose values are numbers, but numbers that skip over things, right? There are gaps that don't make sense, right? Frequently, discrete variables are made up of counting things, where only whole numbers make sense and fractions don't. There are other types of discrete variables, but that's an example, the most common example of what we have there. And these are given names that are capital letters near the end of the alphabet. So capital X and capital Y tend to be the type of things that are given, the type of names that are given to discrete random variables. And then lowercase x's and y's are the individual values. Right, so that's just some notation as far as how this sort of thing goes. And the other main definition that we have here is a probability distribution. There we go. So this is a table or a formula. It's generically often given as a table, but there are some very specific types of random variables that have names that we have formulas to go along with. So a table or a formula that gives a probability for each value of a random variable. And there are two rules for random variables in general. The first rule is that 0 is less than the probability that the random variable is equal to one particular value is less than or equal to 1, right? So this is similar to what we talked about before, where instead of having this x equals x, we had e there, right, for event. And you could think of this, a random variable equaling a particular value as being a very specific event. And that is in fact what it is, and that's why these rules are so similar. And the other thing that has to be true is that the sum of all the probabilities for x equaling all the values of x has to add up to 1, right? Something has to happen, right? Remember, our definition of experiment is something we can repeat that always has an outcome from the sample space. So if we add up all the probabilities of all the different outcomes, all the different values, then we get everything, because something is guaranteed to happen by the definition of experiment. There are a couple of things we can do with this. We can find the expected value, right, which is notated like this. It's also notated like this with mu, and that's because another way to say expected value is the mean of a probability distribution. And our definition for that is the sum of the individual data values by the probability that the random variable is equal to that data value. Right? And the reason for that language, I said this was the expected value. And so that is the number you might expect to get on average if you repeat the experiment a lot. Right, that's related to the law of large numbers that we talked about in the previous chapter, where the classical probability equals the experimental probability once you run the experiment many times. Right, so that's sort of the idea that we have here, is that if you run the experiment many times, then you will get the expected value on average, right? And the more times you run it, the closer you're going to get to that expected value. We also can talk about the variance of a random variable, and that's also called sigma squared, because it's the same variance we talked about at the beginning of the class. And there's two different formulas we have here. One is very similar to the formula we had for variance of data, right, where we have xi minus mu and then we square all of those. But then we can also write this as the sum of the xi squared times the probability that x equals xi. And then we add all those up, and then we subtract the average squared. Right, so both of those are equally fine ways of getting it. It's just whichever one seems easier to you. Right, and then the standard deviation right, so this is the standard deviation. This is the variance, right? And those are both the same idea as we had before. Right, so let's work on some problems here. Right, so we're going to look at which of the following probability distributions are valid. Right? In other words, which of them follow the rules. So, let's see. And let me do one more here. All right. So as we look through these, looking at this one first, right, if you're trying to determine whether a table gives you a probability distribution, the first column doesn't tell you anything, right? There's no restriction on what the first column could be, I guess, except technically it has to be numbers, right? But as long as it's numbers, then that's fine, right? So we really need to be looking at these probabilities, right? And the first one was that all of the probabilities are between 0 and 1. And that's definitely true. So rule 1, we got. Rule 2 says that if we add up all the probabilities, right, we should get 1. So what happens when we add them up here? We get 0.1 plus 0.2 is 0.3. 0.3 plus 0.3 is 0.6. 0.6 plus 0.2 is 0.8. And that's no good, right? We need, when we add up everything in that column, we need it to equal 1. Right? So, looking at this one over here, the next one as we go across the page, right? This one we can kind of see right away that it fails number 1, right? Specifically because of that value is less than 0. And rule number 1 says that all of our values have to be between 0 and 1. Now, the sum of all the probabilities does actually wind up being 1, so that's okay, but this is still not a distribution because both rules have to be true. Right, so this fails to be a distribution because of the first one. Right, so looking down here to the bottom left, our first rule is good. All of those numbers are in between 0 and 1. And when we add up all of the probabilities, we get 0.2 plus 0.3 is 0.5. 0.5 plus 0.2 is 0.7. 0.7 plus 0.3 is 1. So this one is a valid distribution, right? And over here, looking at our last one, 1 is still good. 2, if we add up all these probabilities, we get 1.5, right? So in this case, that's too big because we need it to be equal to exactly 1. So this guy is also not a probability distribution, right? So this is the only valid probability distribution that we found here out of these 4. So problem 2, what is the expected value and variance of the above valid distribution? Right? So we're going to be taking this table, this distribution, and finding the expected value and the variance. To find the variance, you have to know the expected value. So I suppose I could have just said find the variance if I wanted to be lazy with my question writing. But we need to find it explicitly. So the expected value of x is the sum of all of the xi's times the probability of getting that xi. So the first x is -2, and its probability is 0.2. Then we need to add the next x times its probability. Then we need to add the next x times its probability. Then we need to add the last x times its probability. Right, so we get -0.4 plus -0.3 plus 0.2 plus 0.6. So that gets us 0.1. Right. So on average, if we repeated whatever this experiment was over and over and over again, we expect to get, on average, about 0.1. Right. Now the variance, right, we could either take the sum of the squares times the probabilities and subtract from that the expected value we just found, because remember, expected value is the same thing as mu. Or we could subtract mu from all of the x values first, then square it, then multiply by the probability. That honestly sounds more complicated to me. So I'm going to decide to do it by the first one. Whichever one you want to do is fine. I need to leave that table there for me, though. So I'm going to use this formula. Right? So that means that I need to add the first x value squared times the probability to get the first x value plus the second x value squared times the probability to get the second x value plus the third x value squared times the probability to get the third x value plus the fourth x value squared times the probability to get the fourth x value. And then from all of that, we need to subtract mu squared. So this is going to be 4 times 0.2 plus 1 times 0.3 plus 1 times 0.2 plus 4 times 0.3 minus 0.01. So this is 0.8 plus 0.3 plus 0.2 plus 1.2 minus 0.01. So we get 2.5 minus 0.01, 2.49. Right, so that's our variance, what we get there. And if we wanted the standard deviation, which this doesn't ask for, but if we wanted it, then we could take the square root of that. But as it stands, this is what the problem asked for. Alrighty. One more problem. Oops, not $1,000, there are 1,000 tickets. 10 of them win $5. 1 wins $500. Right? So, how much could you expect to win on average? Right, so on average and expect are words that tell us that we're probably looking at the expected value of something. Right, and that's going to be the sum of all of our x values times the probability to get each of our x values. But we need to figure out what those x values and those probabilities are from this word problem, right? So if the expect question is about how much do you win, X should be how much you win from a ticket. And here, we're going to make an assumption that it would probably be a good thing if you just gotten the text up here to ask about it. We're going to say we want our net winnings, right? So what are the three different options? The options are 1, our ticket doesn't win anything. 2, our ticket wins $5. Or 3, our ticket wins $500, right? But since we want our net winnings, our potential X values are going to be -1, because if our ticket doesn't win, then we've paid $1, so we are at -$1. The other option is 4, because if our ticket wins $5 and we paid $1 for it, then our net winning is going to be $4. And then it's going to be 499, because if we happen to get the ticket that wins $500, well, we paid $1 for that ticket, so overall our net winnings are 499. Right? So those are the three possible outcomes of the experiment of buying a ticket. Now we need to know the probability for each of these. And generally in a lottery system, it's going to be equally likely to get any one of the tickets, right? So we can go back to classical probability, and we can say, okay, the total number of outcomes, total number of tickets for all of these is 1,000, right? One of them got me the $500, which gives me a net 499 winning. 10 of them got me $5, which nets me $4 winnings. That must mean that the other 989 weren't winners, right? Because if 11 of them are some kind of winner, that means the rest of them have to not be winners, right? So our expected value is going to be -1 times 989 over 1,000 plus 4 times 10 over 1,000 plus 499 times 1 over 1,000. So we get -989 over 1,000. We get 40 over 1,000. And we get 499 over 1,000. Now, since those all have a common denominator, we can just combine everything over 1,000. Let's see. So it's definitely going to be a negative number. -450, I believe, is what we get out of that. And so, once we have that, that is our expected value, right? And we can translate this into decimals if we want, right? That's -0.450, or just 45 rather, because this dividing by 1,000 moves the decimal place over 3 times. Or we could just leave it like this, or we could do any manner of canceling that we wanted. But, so all in all, on average, we would lose about 45 cents per ticket, right? Because negative, in terms of net winnings, is going to be losing money, right? Because it's the opposite of winning. And since 1 here counted for $1, the 0.45 is obviously going to be 45 cents. Right? Once we tie it back into the word problem there. Right? So, let's see. Next up, we'll be talking about some specific types of distributions. Like I mentioned up above, generic distributions have these tables, and some distributions happen often enough that they get names and formulas to go along with them. So that's what we'll be dealing with next time, and I will see y'all then.